thank the organisers for inviting me to speak, and also for putting on what has turned out to be a really fascinating workshop. And the essence of my talk is really going to be about the adaptation of the UK electron-molecule scattering codes to treat photoionization. But I'm going to look at it in the context of attosecond spectroscopy and strong field physics and show some results from that area. So what do we mean by attosecond spectroscopy? Firstly, what's an attosecond? I'm sure everyone here knows what an attosecond is. It's thousandths of a femtosecond. It's a really short amount of time, and which I think is illustrated nicely by this this figure here, where you can see that an attosecond to electron motion, which occurs at the attosecond time scale, compares to the fastest human motion in the same way as the fastest human motion compares to somewhere around the age of the universe. So it's really short. And so really the aim and idea of attosecond spectroscopy is to observe and control these electron dynamics at a natural time scale. And one of the key challenges that people have come to realize recently in the strong field community is that many electron dynamics are important. I think that's not news to anyone here. So how do we get this? How do we get this time resolution? So these are two examples of experiments that allow you access to the to attosecond time resolution. So these experiments are generally done by using strong few pulse, strong few femtosecond IR pulses, which can then generate even shorter attosecond, 80 attosecond XUV pulses. And so there's, and it's also normal to work with aligned molecules, so you don't average out the interesting effects you might want to see. So one technique is the attosecond streak camera. I'm not going to say very much about these. I'm just going to quickly go over them. And here you have one photon ionization of a molecule to the continuum, and then and this is done in the presence of a moderately strong IR field. And the subcycle gradient of the field streaks the electron momentum, and from that you can map to a time resolution. In a high harmonic generation, you have some sort of multi-photon tunnel ionization, and then the electron is returned and recombines and emits an XUV pulse. And the time resolution in this situation comes from the fact that again comes from the subcycle gradient of the IR pulse, and comes from the fact that that there's a specific time of birth in the continuum, which then maps onto a specific trajectory in the laser field and the specific return energy at a specific time. So all these techniques really rely on, or theoretical descriptions of these techniques rely on one photon ionization or recombination matrix elements. So with this goal in mind, we decided to adapt our matrix codes to treat this situation. Jonathan gave a very nice overview of the Rmatrix method yesterday, so I don't know if I really need to say too much about this. It's simply I think as everyone knows here, the technique, the main, the power of the techniques comes from dividing the configuration of the space of the molecule in two regions and doing different levels of approximation in the two regions. Yeah. What's happened?
Control L or F L on Linux.
Right. Sure. Oh, no, it's still. Sorry about this. Yeah, this is the result of F5.
It's actually, yeah, exactly. Like, this is Linux. Alt sysrec. Raising elephants is so ugly. Actually, that's how they fixed the part as well. In the Bay Area, they just one time got stuck in the tunnel part, and they just powered the whole thing off. It's really dark, and then powered it back on. It's like, wait, how's that going to fix the brakes? No, we crawled out of the tunnel slower than I could run.
They did that on an airplane.
Yeah.
We have to, it's blinking here, we have to restart.
You went in the air at the time,
Not for long, anyway. I was usually I'm not nervous anymore when the plane goes up, but this time I was.
This was quite some of the early efforts. They didn't fly by wire stuff. And the computer was just waiting behind. So we were in Tenerife, and they said, okay, we'll have to reboot the computer.
Yeah.
Would anybody like to leave the plane? So, people got off the plane, because like, they were scared. And they got off, they take a look at job, and the pilot said, well, they left the plane, but they don't realise that we're the same plane tomorrow.
I was about to hit this slide. Yeah. Yeah. What was wrong? Okay, I seem to be being plagued with technical issues. So, I was about to move on to the next slide. And so a lot of the physics, again, Jonathan gave a nice introduction to this, comes in a region wave functions and exactly how you construct them. So just to briefly remind you, they're constructed in an expansion over target states. So let me call them ionic states because I'm looking at photoionization. So you get an ionic state times a continuum orbital, and then you get these so-called L-squared configurations, which are put in for, well, essentially for technical reasons. Then the whole thing is anti-symmetrized, and you solve the inner region Hamiltonian and get your coefficients. So, what do we need to do to adapt the Rmatrix to photoionization? The Rmatrix method to photoionization. There are really two technical challenges in adapting the UK Rmatrix codes. And I'm going to talk a little bit about both of them. The first challenge is that the explicit form of the scattering wave function is not calculated in the inner region. Essentially, we need the scattering wave function expanded in this inner region basis of psi sub k that was on the last slide. And the second problem is that we also need dipoles between those inner region wave functions. And the problem here comes from the fact that you have two different types of basis function in that expansion. One is the L squared, as I showed you, and the other is the ionic state times a continuum orbital. And the problem in this is the ionic state is actually a multi-configurational state. It's, in general, it's produced by some CI procedure. And then, so what this means is that we can't use the existing dipole code for calculating bound transitions, because these contracted basis functions don't obey Slater's law. So this has led to a new module called CDEMPROP. And I'm just going to describe how this works. So this is some quite technical detail. So what is our goal? Our goal is to calculate a transition dipole between a bound state and a scattering state. From that, we can get all the photonization or recombination observables that we're interested in. And I'm only going to consider bound states which are fully contained within the inner region. And this means that the bound state in this integral essentially filters the inner region. We only have to consider dipoles in the inner region. We don't have to worry about the out-of-region dipoles. So, of course, we expand the scattering wave function in terms of these inner region wave functions of psi k, which I'll show again here. And we also want the bound states in the same basis. And so, and actually, of course, we can expand these further. So the task is really to calculate dipole matrix elements between this initial basis and the inner region. And I'll just show you how we do this on the next slide. So this is the dipole operator represented in this initial inner region basis. And so the green block here just involves the L-squared configurations and can be constructed with existing code. But the red blocks require a little bit more work. So if we first have a look at the contracted blocks, so it's the dipole between two different contracted basis functions, then what we find is actually quite nicely, if we integrate out all the electron coordinates except for one, then this reduces to just a single electron integral between two continuum orbitals, which is only non-zero when the target states are equal, plus transition dipoles between bound states of the ion, which is only non-zero when the continuum orbitals are equal. And then let's move on to the contracted, to the off-diagonal blocks, which involve both contracted and L2 basis functions. And here we integrate out all of the electronic coordinates except for one, and we end up with a one electron integral between a continuum orbital and what looks very much like a Dyson orbital. This is the Dyson orbital. It's the overlap of the ionic state plus an electron configuration. And the nice thing about doing it like this is that we can now easily also get, if we want, Dyson orbitals out of the code. So this is all implemented in CDEMPROP. It calculates inner region dipoles and Dyson orbitals, and it's being used at the moment by myself for photoionization and photorecombination. Michael is, I think, currently starting to use it for his photodetachment studies. I'm also using it for input to high harmonic generation codes, and this is the point where you need Dyson orbitals because you need some way of ensuring phase consistency of the dipoles between the two codes. And lastly, it's being used in the development of the time-dependent Rmatrix, which has been developed by John Tennyson and others. So now let's have a look at scattering wave function coefficients. And I'll just very briefly talk about these. These are quite straightforward to calculate. What you need is the asymptotic solutions propagated back to the Rmatrix boundary. This is the radial part. And then you need the Rmatrix itself. And then you need the radial part of the continuum electron that comes from the inner region, also evaluated on the boundary, which known as the boundary amplitudes. And then EK is the energy of the Rmatrix poles, and E is the scattering energy. And then the band state coefficients can be calculated using existing modules in the code. Okay, that was all. Okay, so we we looked at one particular molecule in several different ways, and the molecule we chose to look at was CO2. So we looked at photoionization from the ground state of the neutral, leaving the ion in the lowest four excited states. And these are some details of the calculation. We made target orbitals by doing a mol-pro full valence CAS-SCF calculation, which we then state averaged over 64 states of the ion and one state of the neutral, the ground state of the neutral. And continuum orbitals were constructed in the normal fashion by matching to Coulomb functions, and we included up to the fifth n equals 5 partial wave. And we looked at three different models. We looked at, this is the simplest, basically the simplest possible model. It's a static exchange model. Then we looked at, we also used, this is the largest model, this was the same active space as the mol-pro CAS-SCF calculation. And then we've just looked at single and double excitations within this active space. And we treated both the target states and the neutral in the same fashion with the same active space. For Model 2, we had 96 states, and Model 3, 144 states in the close coupling expansion, and we also added in 3 virtual orbitals for symmetry. So, after all that, now let's have a look at some results. So here, I'm found collated experimental and theoretical results from these 2 papers, so references to the experimental theory can be found in this. And looking first at first channel, and we have red is model 1, which is the static exchange. So red line here. Green is model 2, which is the CISD model, and blue is model 3, which is our full valence CAS model. And well, what you can see here, firstly, in models 2 and 3, there's a whole bunch of autoionizing resonances. They're not very well resolved because I've used quite a coarse energy grid to produce these cross sections. And what you can see, they all kind of lie within somehow all these experimental points. So it's hard to say which is better, really. So moving on to the A channel, then here again you can see that the static exchange model, model 1, seems to give a cross-section, partial cross-section, which is too high in magnitude overall, at least compared to these experimental results, for which I'm not sure exactly what error bars are. But, then we look at model 2 and 3, they give very similar results, and seem to be closer to the experimental results. We're looking at B, and this is here we can see in channel B we can see some more significant differences between our three models, and that what we can see is that the resonance, this low energy resonance position, is worse for model 1, starts to improve for model 2, and gets even better for model 3. Now we come to channel C, and here things really don't look all that like the experiment, I have to say. So what the single channel static exchange model does look like is Robert Lucchese's single channel calculation here, where the resonance is peak is slightly higher. But when we come to model 2 and 3, then the same thing that is seen is actually seen in Robert's 3-channel calculation, is that really the cross section is a lot lower than any of the experimental points here. And in model 2, this resonance position has dropped a lot, and in model 3 it's dropped even more. Okay. So now we're going to turn to looking at some angular distributions. But first I should say a little bit more about high harmonic generation, because what I'm going to compare to is actually a follow-up experiment to the one Robert mentioned in his talk when he was talking about MF pads done by Mark Vracking and others, his experimental group. And it's so, and what they use in this experiment, they use high harmonic generation to provide an XUV source, essentially. So you probably all know this high harmonic generation process. The molecule or atom is exposed to a strong IR laser field, which distorts the molecular potential and allows for tunnel ionization and subsequent propagation and return in the laser field. And when it returns, it can recombine and emit XUV light. So let's look a little bit about, let's look at some experimental details. So in this experiment, firstly they align their molecules, and they have two different alignments, what they call aligned and anti-aligned. So aligned is aligned with parallel to the direction of the IR field, and anti-aligned is planar to localized, perpendicular to the direction of the alignment field. Now, the difference between this experiment and the previous experiment that they did and that Robert talked about is that instead of having their XUV pulse parallel to their aligning laser, they have it perpendicular. And So what they did is they came in with an XUV pulse, which they measured to contain harmonics in the range from 11 to the 29th, which gives an energy range of about 17 to 45 eV. And they ionized their aligned molecules, and then they do this in a they then detect the molecules over here using a velocity map imaging spectrometer. The degree of their alignment, as Robert mentioned actually the other day, is really quite low. And because of that, they tried to recover angular structure by looking at the difference of the aligned and anti-aligned signal. And what they found in the previous experiment is that the lowest 4 channels are dominant in the angular distributions. So what I calculated was angular distributions orientationally averaged over the experimental alignment distributions. And then one of the experimentalists, Arnaud Rouzy, combined this with the experimental harmonic intensities and found a difference and projected onto this 2D screen, so they projected to 2D so they can compare with what they see on their detector. And let's have a look what it looks like. So in the experiment, they have, you can see there's a lot of, there's a ring structure. And this corresponds to the harmonics, which are in the XUV pulse. You can see red and blue regions. The red regions are when the aligned cross-section dominates, and the blue regions are where the anti-aligned cross-section dominates. So let's have a look now at how theory reproduces this experiment. So there's one more thing I should say is that, I mean, what's being measured here is radial distance on the detector, and as you go outwards in the radial distance, then that corresponds to increased energy in the photoelectron spectrum. So when we look at the theory, now this theory is for my Model 2. We can see that seems to be like, at least looking at it in this sort of carpet plot style fashion, that seems to be reasonable agreement, at least qualitatively. And now if we look at it in polar coordinates, we can see a little bit better that we do seem to have quite good agreement between experiment and theory. And we've also have some cuts here at 0 degrees and also at 90 degrees, which at 0 degrees the match seems to be between theory and experiment. Experiment in red and theory in black seems to be really quite nice. Although it's a little off at 90 degrees. These peaks appear to be a little too high and a little too. And if you look at this, they seem to be a little too sharp a peak as well, a little too narrow. I'll now have a look at my Model 3. And if anything, Model 3 seems to be a little bit worse. You can see there's some features here different in the theory that doesn't appear to be there in the experiment. And there's also seems to be actually some extra angular feature here coming in the theory that there's also doesn't look like it's in the experiment. But I should say that all these results are preliminary results. I'm still working on improving the models. I guess these are just, these angular distributions are not converged yet. So, how am I doing for time?
It's about 5 minutes.
About 5 minutes, okay. So then I shall actually, okay, I think it should be okay. So now I'm going to look at, so now we decided to look at actually using dipole matrix elements from the Rmatrix codes to calculate harmonics. And there's one particular thing that there's one aspect that we're interested in looking at harmonics, and that is that you can think of the ionization process in harmonics. Firstly, as a multi-channel process, so it can create a whole wave packet during ionization, and obviously this means that you have relative phases between the various channels that have been excited during ionization. And then you get, during the subsequent propagation in the laser field, this whole system keeps on evolving in the laser field and gets and accumulates more phases in the different channels. And then when it recombines, because you start off from the same your initial and final state are the same state, the ground state of the neutral, you can have different interfering pathways which record these phases that evolve coherently during the whole harmonic process. And those phases actually get mapped onto amplitude modulations of the harmonic signal. And this is one of the reasons why I mentioned that we really need Dyson orbitals to ensure phase consistency between our harmonics codes and the Rmatrix codes, because we're really looking at these phases and trying to identify what this ionization phase is. So we know the recombination phase. We can calculate numerically this phase due to evolution of the system whilst the electron is essentially free. But the ionization phase is more tricky to calculate or to get at. So we look at harmonics harmonics produced for CO2. The intensity of the IR field is relatively low. I think it uses a 40-second pulse, and this was done in the group of Jan Mares, who's at Celia in Bordeaux. I should make a comment, actually, another comment about alignment here is that although the alignment in Mark's experiment was not very good, people are capable of doing a lot better alignment in these experiments, and they can. I think in Mark's experiment it was in the tens of degrees that the angular spread, but people can get down to a few degrees. And Jan Mares is actually pretty good at doing this. So here we have the experimental harmonics. And we just have between minus 50 and 50 degrees measured here. And we have intensity here, and this is harmonic number, of course. And what we see when we do some quite involved calculation is that harmonic, that if we put in by hand some ionization phases, or we need to put in by hand some ionization phases, really to match the experiment. If we, for example, just consider all the initial phases as zero, then the harmonics really look nothing like what we see in the experiment. But this is very preliminary stuff, and in these calculations, we just use our single-channel static exchange matrix elements, and we need to have a look at the more complicated models and see what effect this has. And I think I'll skip my last slide. And thank you for your attention.
Thanks to Michal for making this talk possible.
Yes.
So, any questions?
So I have one comment on the CO2 is that if you really want to make experiment very degree, I suspect you need to put vibrate the average over the ground state. I mean, Bill McCurdy showed that C state bump goes away when you put bending and things like this.
Yeah. No, I agree with that. Yeah. For sure.
Slava.
I have a simple question that I asked Jonathan sometime before. Is Rmatrix able now to calculate a transition type of moments between continuum and ground states?
Yes.
Is it standard feature Rmatrix?
I mean, it's what I developed to do this work, and it's in the repository, so it's kind of in beta format. So it's in beta format. So it's yeah.
Some are more beta-rich than others.
No, it's in a pretty good state. So if you want to use it, you can use it. And,
What form do you use for the dipole operator?
length gauge.
In the high harmonic calculations also?
Also in the harmonic calculations, yeah. The length form of the dipole operator.
Yeah, I have a general question. I actually don't understand why is it all relevant to attosecond physics, because you just calculate photoionization. So you calculate matrix element of dipole operator between stationary states. So what does it have to do with attosecond spectroscopy?
Maybe I didn't get this point across very clearly. All theoretical techniques in strong field physics and attosecond spectroscopy, apart from solving the full time-dependent Schrödinger equation, use field-free recombination or photoionization matrix elements in part of the just to model that part of the process.
So use this as an input for...
Yeah, so this is one input to the harmonic generation codes.
Okay. Any more questions? There is no questions. But thanks our speaker again.